Good evening, everyone. Myself, I'm Faaiz. I'm from AIIMS Nagpur. Yeah, our topic is for today rotational motion part 2. Okay, we have already seen the part 1. Okay, today we will discuss about part 2. Okay, in part 2, we will see relation between torque and angular acceleration. We will get into angular momentum. Okay, then we will see conservation of angular momentum, then rolling motion, kinetic energy of rolling motion. Okay, so let's directly see what is the relation between torque and angular acceleration. See, likewise in kinematics, we studied what, yeah, F F net equal to M into A. Yeah, same way we can write torque equal to I into alpha, right? Or torque net equal to I into alpha, where alpha is angular acceleration where alpha is angular acceleration and I is moment of inertia. Moment of inertia. Okay. So see, this is the first question. Okay. Let me read the question. A string is wrapped around the rim of a wheel of moment of inertia. Okay, string is wrapped here, right? String is wrapped here. Moment of inertia is actually 0 point. See, 0 point is here, 0 0.2, 0 0.2. Okay. And radius is 20 centimeter. The wheel is free to rotate about its axis. Okay. Initially, the wheel is at rest. The string is now pulled by a force of 20 Newton. Find the angular velocity of the wheel after 5 seconds. Okay. And this is the application of which formula? Tau equal to I alpha. See here. First, see here. Okay. Force is applying here, right? F is equal to 20 Newton is applying here. So torque will be how much? We know that torque equal to F into force into R perpendicular, right? ഇവിടെ R perpendicular എന്ന് പറഞ്ഞാൽ ഇതല്ലേ? That means എന്താണത്? Radius of this wheel ആയിരിക്കൂലേ? Radius ആയിരിക്കും. Okay. About its axis. Suppose ഇവിടെ axis okay. So torque will be how much torque will be F into F is 20 Newton. 20 Newton into perpendicular distance means radius. Okay, so 20 centimeter means 0.2 meter. Right. So it will be 4 Newton meter. This will be the torque. Okay. This will be the torque. Okay. Next, we have to find out what? See, moment of inertia about its axis is given. Moment of inertia is given 0.2. So moment of inertia we know 0. Okay. So by applying tau equal to I alpha, so 4 equal to 0.2 into alpha. So alpha will be how much? Alpha will be 4 divided by 0.2, 40 by 2, that is 20. Right? 20 radian per second square. This will be the alpha. Okay. So we got alpha. And we have to find out what? We have to find the angular velocity of the wheel after 5 seconds. The wheel is at rest initially. So yeah, we can apply which equation? Omega naught equal to omega equal to v equal to u plus at. Omega equal to omega naught plus at here alpha t. Okay. So omega equal to omega naught is 0 initially. Wheel is at rest. Alpha we know 20. Time period is given 5. This will be 100 radian per second. So which option is correct? Yeah, option B will be the correct answer. Okay. Yeah. Next, let's solve a previous year question. A rigid massless rod of length 3L has two masses attached at each end as shown in figure. Right, 2m0 here, 5m0 here. The rod is pivoted at point P here on the horizontal axis. When released from initial horizontal position, its instantaneous angular acceleration will see because of this mass 2m0 and 5m0 at point P. Yeah, if this system is released, there will be a torque, right? So let's see what is the torque about axis or about point P, right? Okay, so see, this is the system, right? Here is the point P. Okay, yeah, there is the point P. Here 5 mg will act downwards. Okay, mg. Okay, I'm taking m0g, right? Here how much? Okay, here how much? 2 mg, right? 2 mg. This distance is 2L. This distance is L. Okay, and yeah, torque due to 5 mg will be in which direction? Yeah, this direction, right? And torque to 2 mg will be this direction. For these torque will get subtracted. Okay. So net torque will be torque net about P will be 5 mg into L. Yeah, L is the perpendicular distance from point P minus 2 mg into 2L, 5 mgl minus 4 mgl, that is mgl. This will be the net torque. Okay, when the system is released. Okay. And next we have to find out I, we know tau is equal to I alpha. For that, we have to find out alpha. So next step is, yeah, we have to find out what is moment of inertia about P. Moment of inertia about P will be, yeah, this is a massless rod. This is a massless rod. So there is no, so just to add moment of inertia of these masses. So how much? 5m0 into L square plus 2m0 into 2L square, that is 4L square. This will be how much? 5ml square, 8ml square, that is 13m0L square. Okay, so we got I, we got tau. So next we can apply tau equal to I alpha, that is m0 into GL equal to 13m0L square into I into alpha. So alpha will be m0 we can cut, L we can cut, alpha equal to how much? G divided by 13L. G divided by 13L. So option A will be the correct answer. Okay. Okay, let's solve next question. Uniform rod AB. Okay, this is the rod AB is hinged at end A in horizontal position as shown in the figure. The other end is connected to a block through a massless string as shown. Okay. The pulley is smooth and massless. Masses of the block and the rod is the same. Okay, mm. Okay, equal to m. Then acceleration of block just after release from the position is okay. Okay. Okay, if we release this system, no, let me draw the free body diagram here. See, forces will be, okay, mg will act downwards, right, and tension T will act here. Okay, same tension T will act here also, right, and here will be mg, right. Okay, these are the various forces. Okay, so on block M, this is the block M. Okay, block M will move downwards, right? If the system is released, so its net acceleration will be a downwards. The net force acting is mg downwards and tension upwards. So we will get an equation here, mg minus T equal to M into A. Okay. So we will need this equation at the end. Okay. Mg minus T. Okay, this equation we got. Right. Next is, let's resolve about rod. Okay. What is the condition about rod? This is the rod. Okay. The forces acting on rod are here T, tension T is acting right. And length of the rod is L. So this is L by 2. This is L by 2. And mg is acting downwards. Okay. So the net torque, if this is the hinge point, right? This is the hinge point H. So torque about the hinge point will be how much? Torque about hinge point will be, mg. So torque due to tension will be which direction? Torque due to tension will be this direction, and torque due to mg will be this direction, right? Right. R cross F. Okay. R cross F. Okay. Both are in opposite direction. Okay. So we have to minus. We have to subtract. So net torque will be T into L, the distance, minus mg into L by 2. Okay. Mg into L by 2. So L is common here. T minus mg by 2 into L. This is the net torque. Okay. This will be equal to tau equal to I alpha. The rod is rotating about its one end, right? So what will be the moment of inertia? ml square by 3. So ml square by 3 into alpha. Okay. Here we will get an equation for alpha. Okay. Before that, see, at here, see, this point has a circular motion, right? Right. So we know that what A equal to R alpha. So here alpha, we can also write A divided by length L. Okay. Because this point will follow a circular motion when the road goes upwards. So and its radius is L. So acceleration A will be R alpha. So T minus mg by 2 into L, which is equal to ml square by 3 into alpha, we can write A by L. Okay. See. So L we can cut here one L. Okay. So both L gone. So tension T will be M by 3, MA by 3 plus MG by 2. MA by 3 plus MG by 2. Okay. What we have to find? We have to find the acceleration. Okay. We have to find the acceleration of the block. Okay. For that, so we got tension now. So we have this equation, right? So mg minus tension, we can write MA by 3 minus mg by 2 equal to MA. So MA, okay, so mg minus mg by 2, mg by 2, which is equal to MA plus MA plus MA by 3. That is 4 MA by 3. So we can cancel. So acceleration A will be 3g divided by 8. 3g divided by 8. So our option C will be the right answer. Next, let's see what is angular momentum for a point mass. What is angular momentum for a point mass? Suppose, we have a mass M moving with velocity V. Okay. I have to find out angular momentum about a point O here. Okay. How can I find? Again, simple. What should I do? Okay. Should extend the velocity vector and find the, yes, R perpendicular. So yes, angular momentum will be linear momentum mv into R perpendicular. Okay. mv into R perpendicular. mv into R perpendicular. Okay. mv into R perpendicular. Okay. And we know that vector angular momentum vector L is equal to vector R cross. So we got two equations, R cross P and, yeah, P into R perpendicular. Simple for point mass. Let's see one question. This is the question. Two small balls A and B, each of mass 1 kg, are attached rigidly to the ends of a light rod of length d equal to 2 meter. Okay. One mass is here, one mass is here, both having 1 kg mass. As the structure rotates about the perpendicular bisector of the rod, okay, at an angular speed. So it's rotating about this axis, perpendicular bisector. Omega is given. We have to find out to calculate the angular momentum of the system about the axis of rotation. We have to find out, okay, calculate the angular momentum. So let's see. Okay, let draw the condition. Let me draw first. So one rod is here, one mass is here, one ball is here, another ball is here. Each of mass m. I'm taking mass m. At d by 2 distance, is given as this is, okay, this is rotating with omega angular velocity. Okay. So if it is rotating with omega angular velocity, right? So here at this point, this m will feel a velocity, right? That will be mv upwards. Here it will be mv downwards. And here v will be r omega. Right? Simple. Very simple, right? Okay. So we got linear momentum of mass m and the linear momentum of mass m here also, mv. But direction is different, right? What we have to find out? We have to find out angular momentum. So angular momentum is, we know angular momentum L equal to mv into r perpendicular. Okay, here r perpendicular is d by 2. That will be mv d by 2. So because of this first mass and second mass, the direction of angular momentum will be which direction? Okay, this direction. And this mv also angular momentum will be this direction. Okay, r cross f. Just do r cross f. Sorry, r cross p here, right? R cross p. Okay, r cross p. Okay, both are upwards. So just angular momentum we can add. So m into v into d by 2 into 2 because 2 masses, right? That will be mvd. Okay, and we can write m into, we can write r omega, right? So here is r is d by 2. So d by 2 omega into t. Okay, how much? M d square omega by 2. So just substitute those values. M is 1. So 1 into d is 2 meter. So 4. Omega is 10 by 2. 40 by 2. That is 20. Okay. Option B, 20 will be the right answer. Okay. We have a beautiful question next. A particle is projected at time t equal to 0 from a point P with a speed V0 at an angle of 45 degrees to the horizontal. Right. Find the magnitude and the direction of the angular momentum of the particle at maximum height. Projectile motion, I have to find out angular momentum at maximum height and when it hits the ground again. So first, let's see when it gets maximum height. When the projectile is at its maximum height, when the projectile is at its maximum height, okay, this is the maximum height, okay, this will be h max. Okay, when projectile is at maximum height, it got only one velocity. U sin theta will be 0, right? So it got only u cos theta. Okay, u sin theta will be 0 at its highest point. So we know the velocity here, and this is the axis. About this axis, we have to find out the angular momentum, and the perpendicular distance from this axis is h max. So in first case, L will be m into u into cos theta. Mu cos theta into r perpendicular here will be h max. What is equation for h max? U square sine square theta divided by 2g. Okay, this is u and this is theta. U square sine square theta by 2g. This will be the equation at highest point, h max. Next is when it hits the ground. When it hits the ground. Okay, when it hits the ground. Okay, when it hits the ground, this is the condition, right? Okay, you got two component, right? Yes, along x-axis u cos theta, along y-axis u sin theta, along minus y-axis theta u. Okay, and because of this u cos theta at point P, there won't be any angular momentum because r perpendicular is 0, right? And because of u sin theta, the perpendicular distance is horizontal range r. So here L will be mu sin theta into horizontal range r. Okay, what is the formula of horizontal range? Mu sin theta into u square sine 2 theta divided by g. So we got angular momentum when it hits the ground and when it's at its maximum height also. Okay, easy. Yeah. Let's see next what is angular momentum for a rotating body. For a rotating body, what is angular momentum? Okay, very simple. Just a formula only. Let me draw a diagram first. Okay, if this is our body. This is the okay. Through this axis, okay, moment of inertia is I. It is rotating with angular velocity omega. Then it's okay. Angular momentum for a body equal to rotating body equal to I omega. Just P equal to mv, L equal to I omega. Okay, easy. Yes. Okay. So let's solve previous year question here. Okay, this is the question. 4 point masses, each of mass m, are fixed at the corners of a square of side L. Okay, the square is rotating with angular velocity omega, with angular frequency omega. That will be angular velocity omega, right? About an axis passing through one of the corners of the square and parallel to its diagonal, as shown in the figure. The angular momentum of the square about the axis. Okay, this is velocity. Let's solve this. First, let me draw the condition. Okay, square of side L. Square of side L. 4 masses here. Each of mass M having same mass. Okay. Next we have to find out. Okay, which axis? This is the axis. This is the axis. Okay. So we have to find out angular momentum. Angular momentum L equal to I omega. So I about this axis will be how much? Okay, mass M is here, mass M is here, mass M is here. Okay, if sides are L, 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 so the distance of this mass from axis is L by root 2. Here also L by root 2, and this distance diagonal will be root 2 L. So moment of inertia I will be how much? M into L by root 2 square into 2. Okay, same case. This M plus M into root 2L whole square. This will be how much? ML square plus 2ml square, that is 3ml square. Okay, so we got moment of inertia. What you have to find? You have to find angular momentum. Angular momentum equation is I omega. We know I is 3ml square. Omega is given in the question. So 3ml square omega. So answer will be 3ml square omega. So option C is the correct answer. See, very simple question, right? Yes. Let's solve this question. A uniform rod of mass 4 kg and length L equal to 60 centimeter is kept vertical with the lower end clamped. Okay, kept vertical. So it is likely pushed to let it fall down under gravity, right? When its angular momentum when the rod is passing through its lowest position. Yeah, when the rod reaches lowest position, we have to find out angular momentum. Okay. Let me draw the situation first, right? Okay. This is the situation. We have a road here. Okay. This is the clamp. This is the final position of the road. Okay. This is the center of mass of the road. Mass of the road is length of the road is L. So center of mass is L by 2 from the hinge. L by 2, L by 2. Here omega is 0 because initially at rest, here it will have some omega. Right, some angular velocity. So by energy conservation theorem, what we can write? We can write, okay, at the beginning, only it has potential energy, that is mg into L by 2. If I'm taking this as a reference point, okay, mg L by 2. No kinetic energy there. Okay, final condition, when it reaches the lowest position, its potential energy is minus mg into, okay, mg into minus L by 2, right? Okay, because this is the reference point. Plus, it has got some kinetic energy also, half I omega square. Okay. And it is rotating. Rod is rotating at its one end. So I of the rod will be ml square by 3. So mgl by 2 plus mgl by 2, how much? Mgl is equal to half into I is ml square by 3 into omega square. Okay, I'm taking half this side. So we will get 2mgl equal to ml square by 3 omega square. So we can cut ml. So omega square equal to 6g upon L. So omega equal to root of 6g upon L. Okay, this is the angular velocity when the rod reaches at its lowest point. Okay, root of 6g by L. And we have given g is, okay, I'm taking g is 10 and length of the road is 60 centimeter. 60 centimeter means 0.6 meter. Okay, so omega will be how much? Omega will be root of 60 upon 0.6, that is root of 100. It is 10 radian per second, right? 60 by 6 is 60 by 0.6 is 100. Root 100, 10 radian per second. So find angular momentum. So angular for angular, right? What is the formula for angular? Equal to I omega. L equal to I omega. Okay, omega we know. I will be, it's rotating Rod is rotating about at its one end, right? So ml square by 3 into omega. Just put those values. M is how much? M is okay. M is for length is 0.6 in meter. So 4 into 0.6 into 0.6. That is how much? 0.6 into 0.6, 0.36. Okay, ml square. We got ml square by 3 into omega is 10. So we can cut 0.36. So it will be 0.12. So 4 into 12, how much? 48 into 10. Okay, so 4.8. Okay, so L will be 4.8. So which option is the correct option? Yeah, option D is the correct option. Next. Okay. Next, let's see conservation of angular momentum. Conservation of angular momentum. We know that what is conservation of linear momentum, right? As similar, see, if net external torque, net external torque is zero. Net external torque is zero. Yes, angular momentum of the system will be constant. Likewise, we have studied in kinematics, if net external force is zero, linear momentum is constant. Here, net external torque is zero, then angular momentum of the system will be constant. Okay, if let's solve one question. This is the first question. Length L is suspended from a vertical support. Okay. Okay, some part is okay in this question. Okay, sorry for that. Okay, here a bob of mass M attached to a string of length L, suspended from a vertical support. The bob rotates in a horizontal circle with angular speed omega is given. But what about the point of suspension? We have to find out angular momentum. Right. See. So here velocity will be which direction of the mass? This direction. Okay. Tangential. Right. Because of this velocity, velocity will be tangential. Okay. There is a momentum mv, and this is the momentum. Okay. So angular momentum at its about the point of suspension will be okay. If this is the position vector r. So angular momentum at P will be R cross MV, right? R cross P. So its direction will be L, this direction. And if the mass M reaches here, okay, its velocity will be this direction. So our position vector. So at this condition, angular momentum will be same in magnitude but different in direction. So angular momentum changes in direction but not in magnitude. Okay, just MV will be same, that is magnitude will be same. Direction will be different because of velocity direction is changing, and we do R cross P, then we will get L. Okay, here directions of L is changing. Just to do R cross P here, R cross P. Okay, this direction. Okay, yeah. This is our next question. A wheel is rotating freely with an angular speed omega on a shaft. The moment of inertia of the wheel is I. Okay, moment of inertia of the wheel is I. and moment of inertia of the shaft is negligible. Okay. Another wheel of moment of inertia 3I initially at rest is suddenly coupled to the same shaft. The resultant fractional loss in the kinetic energy of the system is. See here. Let me picturize. So, question it is given that initially moment of inertia of the wheel is how much I, and there will be a angular velocity that's omega. Okay. Okay. After that, a 3I. Okay. Another wheel of moment of inertia 3I coupled to the same shaft. Here, who came? Another wheel having moment of inertia 3I. So definitely omega will change. Angular velocity will some omega dash will be there. By see here there is no external net torque. External torque is zero here. So what we can write? Yeah, by angular momentum conservation we can write I initial into omega initial will be equal to I final into omega final. Here what is initial moment of inertia I and initial angular velocity omega. What is final moment of inertia here? 3I plus I, right? 4I into omega final. This will be so omega final angular velocity will be how much? Initial angular velocity divided by 4. That is omega dash will be omega by 4. Okay. Simple. What were to find? Fractional loss in kinetic energy, right? So fractional loss means delta Ke upon initial kinetic energy. Okay, change in kinetic energy is kinetic energy final minus kinetic energy initial divided by initial kinetic energy. For that, you have to find out initial kinetic energy also and final kinetic energy also, right? Okay, initial kinetic energy will be half I omega square, right? Initial kinetic energy will be half into I into omega square. Final kinetic energy will be half into moment of inertia is 4I. Omega square is omega by 4, that means omega square upon 16. So here it will be I omega square by 2. Here it will be 4. I omega square upon 8. So we got final initial kinetic energy. So just apply this equation, final minus initial. So 1 by 8 minus 1 by 2 I omega square, right? Divided by I omega square into 1 by 2. So I omega we can cut. So fraction loss will be 1 by 8 minus 1 by 2. How much? 2 minus 8 minus 6 divided by 16 into 2. That is minus 12 upon 16. That is minus 3 by 4. Why minus? Because it is fractional loss in kinetic energy. Okay, minus indicate loss in kinetic energy. And we got 3 by 4. So our answer will be option D, 3 by 4. Okay, let's solve next question. This is a question. Two coaxial disks having moments of inertia I1 by 2 are rotating with the respective angular velocities omega 1 by 2 about their common axis. They are brought in contact with each other and thereafter they are rotated with a common angular velocity. Easy. If EF and EI are the final and initial total energies, then EF minus EI. Almost similar kind of question. Let's solve. First, let's picturize and then let's solve. Okay, this is the first condition, right? Rotating speed, angular velocity is omega 1, moment of inertia is I1. Okay, next case, angular velocity, moment of inertia is I1 by 2, rotating with angular velocity omega 2. Okay. So next, what are they doing? These both the coaxial disks brought in contact. So the final condition will be it will rotate. Final condition will be it will, moment of inertia will be I1 plus I1 by 2. That is how much? 3 I1 by 2. It will rotate some angular velocity omega. Okay, this is a condition. So by conserving, there is no net torque. So by conserving angular momentum, by initial angular momentum will be how much? I1 omega 1 plus I1 by 2 omega 2 equal to final angular momentum 3 I1 by 2 into omega. Okay. Okay, omega 2 is omega 1 by 2. So omega 2 is omega 1 by 2. So we will get I1 omega 1 plus I1 by 2 omega by 2. That is how much? 5 by 4 I1 omega 1 equal to 3 by 2 I1 omega. I1 cancel. So omega will be how much? 2 we can cancel. So 5 by 6, right? Yes. 5 by 6 omega 1. This will be the final angular velocity. 5 by 6 omega 1. Okay, so we got angular velocity final. So next, we have to find out E final. Okay, energy. Kinetic energy will be how much? Half into moment of inertia is 3 I1 by 2, 3 I1 by 2 into omega square, right? That is 5 by 6 omega 1 square. That is 25 divided by 36 omega 1 square. Okay. This will be what all we can cut here. We can cut 3, 12. This will be 25 divided by 4 into 12, 48 omega 1 square. I1 omega 1 square. 12, 24, 24 into 2, 48. Okay. And what is initial kinetic energy? Initial kinetic energy will be kinetic energy of both the disk. Half into I1 omega 1 square plus half into I1 by 2 into omega 2 square. Omega 2 is omega 1 by 2. So omega 1 square divided by 4. This will be how much? I1 omega 1 square we can take outside. 1 by 2 plus 1 by 4, 1 by 16. Right. So how much? 18 divided by 16 plus 18 divided by 32. So we can cut 9, 16. So 9 by 16 into I1 omega 1 square. This is the initial kinetic energy. We have to do initial minus final. So initial minus final. If we do that, we have to do final minus initial, right? We have to do final minus initial. So final minus initial, let's see. 25 by 48 minus 9 by 16 I1 omega 1 square. Okay. We have to solve 25 by 48 minus, okay, 16 we can write 16 into 3, 48. So 48. So I'm multiplying 27. So how much? 25 minus 27 minus 2. Minus 2 by 48 or minus 1 by 24. So answer will be minus 1 by 24. Yes, minus 1 by 24 into I1 omega 1 square. Which option is correct? Minus 1 by 24. Yes, I1 omega 1 square. Yeah, option D. Option D is the correct answer. That's all. Next question. A thin uniform bar of length L and mass 8m, lie on a smooth horizontal table. 2 point masses 2m and 2m moving in the same horizontal plane from opposite sides of the bar with the speeds 2v and v respectively. The masses stick to the bar after collision at a distance L by 3, L by 6 respectively. If the bar starts rotating about its center of mass as a result of collision, the angular speed of the bar will be angular speed of the bar. Okay, let's quickly solve this question. See, okay, the condition is, okay, we have a bar here. Okay, so from L/3 distance, mass m with the speed 2v. Okay, so inner momentum is 2mv here, right? And here at L by, oh, oops, oops. Okay, at L by 6 distance, mass with 2m, velocity is v. So again here also 2mv, the momentum. Okay, momentum because of the mass coming with the velocity. This is the center. Okay. Next, let's see. This is the O point. So here, because of this 2mv, momentum will be angular momentum this direction, and this 2mv also this direction. This is same direction. So just add up. We can write what? Initial angular momentum will be 2mv into perpendicular distance L by 6 plus 2mv into perpendicular distance L by 3. So we can take out 2mvl common, 1 by 6 plus 1 by 3. How much? 2mvl into 9 by 18, that is 1 by 2, that is 2 we can cut mvl. So L initially is mvl. Okay. And L final will be how much? L final will be I omega. Right. I omega means rod will rotate. Okay, rod will rotate to this axis, right? So I, we can have to find out moment of inertia I. Moment of inertia I will be how much? ml square by 12. So mass is 8 ml square, 8 ml square by 12 plus, okay, because of this masses, ml square by 9 plus ml square by, okay, it's simple only. We will get then omega multiply, then equate with the initial angular momentum. Okay, simple question only. We'll get option B as the right answer. Okay, so time permit, I will come back to this question. Okay. Okay, next let's see rolling motion. Okay, rolling motion. See, if a body is pure rolling, if body is having pure rolling, okay, if body having pure rolling, what is happening, guys? Okay, if body having pure rolling. Okay. Okay, here I'm taking 4 points. Okay, you have to add a translation plus rotation. Then here will be net speed will be how much? VCM minus R omega. Here VCM will be this direction, R omega will be this direction. Here VCM R omega same direction. Here center of mass VCM only. Here R omega this direction and VCM this direction. For pure rolling, the condition of rolling is what? Condition of rolling is VCM should be equal to R omega. That is VCM minus R omega will be 0. It's a condition of pure rolling. Okay. The energy in rolling motion is actually rolling motion is translational plus rotation, right? Yeah. Translational motion plus rotational motion. It is rolling. Translational motion plus rotational motion. So energy will be kinetic energy will be, or total energy of the rolling body will be, yes, half m into VCM square. That is kinetic energy plus half I omega square. Okay. And we have a condition VCM will be equal to R omega for pure rolling. Okay. We have a question: uniform sphere of mass 500 gram rolls without slipping on a plane horizontal surface with its center moving at a speed of 5 centimeters per second. Its kinetic energy is. So it's a rolling, right? It's a rolling. Rolls. So kinetic energy will be how much? Kinetic energy will be, yeah, kinetic energy will be half m into VCM square plus of I omega square, right? This is a uniform sphere, solid sphere. That is 2 by 5 mr square into omega. We can write VCM by r. Right, VCM by r square. Okay. So kinetic energy turns to be how much? 7 by 10 m into VCM square. 7 by 10 m into VCM square. Easy. See, the condition of rolling is what? VCM is equal to R omega. VCM is equal to R omega. So we can write VCM equal to R omega. We can write omega as VCM by R. There is no dot in that. Okay. We'll get kinetic energy 7 by 10 m into VCM square. Okay. And here it is given that 7 by 10 mass is 500 gram. That is 0.5 kg. VCM is given 505 centimeter per second. That means 5 into 10 raised to minus 2 square. So will be how much? 7 by 10 into 0.5. We can 0.5 into 25 into 10 raised to minus 4. This is turns out to be how much? 25. 7. Yeah. Wait. So how much? So answer will be option A. 8.75. Okay. 8.75 into 10 raised to minus 4. 25. Okay, 35 by 4 into 10 raised to minus 4. 35 by 4 is 8.75. Okay. Easy. Yes. This is our next question. A solid sphere and solid cylinder of identical radii approach an incline with the same linear velocity, both roll without slipping all throughout. Okay, the two climbs heights h sphere and h cylinder on the incline, the ratio of h sphere by h cylinder. Okay, simple. It's a very simple question. Okay, for sphere, we can write what? Yeah, kinetic energy, initial kinetic energy will translate as its potential energy, right? Convert as so mg into h sphere. We know that its total kinetic energy is how much? Okay, previous problem only we said 7 by 10 m into VCM square. Okay, so 7 by 10 m into VCM square is mgh sphere. Okay, so h sphere will be how much? 7 by 10 g VCM square. Okay, likewise, we have to solve for cylinder also. Okay, if we solve for cylinder, kinetic energy will be half into m into VCM square plus half omega square, right? Omega for solid cylinder is how much? For as a disk, that is mr square by 2. M into r square by 2 into VCM omega square. Omega square we can write as VCM by r. VCM by r, right? So VCM square upon r square. It will turns out as half m into VCM square plus r square get cancel 1 by 4 m into VCM square. So m VCM square we can take common, m VCM square we can take common. 1 by 2 plus 1 by 4. How much? 6 by 8. That is 3 mvcm square by 4. Okay. So for solid cylinder, we can write 3 by 4 m into vcm square, which is equal to mgh, m into g into h cylinder. So mm we can cancel. H is 3 by 4 g vcm square. This is h cylinder. We have to find out h sphere minus h cylinder. So h sphere minus h cylinder will be 7 by 10 g by 4, 3 by 4, that is 4g upon 3. Gg we can cancel. 4 4 2 5 14 by 15. Yeah. So our option C will be the right answer. Okay, we have a last concept here: angular momentum of a rolling object. Angular momentum of rolling object will be how much? We see angular momentum of rolling object will be, okay, if this is rolling, radius is r. Okay, vcm, this is omega. So its angular momentum will be, total angular momentum will be m vcm into r perpendicular plus I center of mass into omega. This will be the angular momentum of a rolling object. Okay. So okay, see here calculation, but actually see. So we can write 7 by 10. We can write 7 by 10 into 0.5. We can write 1 by 2 into 25 into 10 raised to minus 4. Okay. So 7 into 25, how much? 16 into 150. Okay. That is 175, right? 175. 175 divided by 20 into 10 raised to minus 4. 175 divided by 20 means 17.5 by 2. That means 8.75 into 10 raised to minus 4. That's how we got, and option A is the right answer. Okay. That's over. And okay. Okay, here. So simply just calculation only. You can calculate how. Moment of inertia of the system will be how much? How much? I will be 8m into L square by 12 plus m into L by 3 square, that is L square by 9, plus 2m into L by 6 square, 2m into L square by 36. Okay. So we can take ml square common. 8 by 12 we can cancel 3 4 2. 2 by 3 plus 1 by 9 plus 18. 1 by 18. Okay. So here also we can take how? So I'm taking 18 common. So 3 into 6, 2 into 6, 12 plus 9 into 2, so 2 plus 1. That is 15 by 18 ml square. 15 by 18 ml square is I. Okay. So 15 by 18 ml square omega, which is equal to mvl, initial momentum. You have to find out what? You have to find out omega, right? You have to find out omega. For omega, Then right here, 1L we can cancel, we can cancel. So omega will be V18 divided by 15L. So 18, 15 we can cancel 6, 5. 6V upon 5L. That's how we got option B as a correct answer. So yeah, discussed everything. So thank you everyone.